Hi everyone, I'm Yuan from University of Waterloo and the University of Lille. Today, I would like to present our work exploring the effects of intended use on targeting in virtual reality, which was done with my supervisors Jerry Kazir from University of Lille, Sylvain Malhia from INRIA, and Edward Lang from University of Waterloo. Target acquisition is one of the most common actions performed in an interactive system. Besides using mouse cursor to select an icon on desktop environments, we commonly perform this interaction on many computing environments, such as a touch-based device, a large external display, or in augmented reality. To understand this acquisition interaction, the Fitts law is commonly used to describe the movement time taken to acquire the target. In Fitts law, movement time is modeled as a linear function of the index of difficulty, or ID, which is the log term of target amplitude and target width. However, target amplitude and width are not the only factors impacting acquisition performance. One factor that may impact target acquisition time is the intended use of the target. By intended use, we refer to manipulations that a user plans to do or will do with the target they acquire. For example, you may want to rotate, scale, or duplicate an object after you acquire it in Blender. Acting on an object is then a compound action comprised of first acquiring it and then performing the manipulation on it. We can then increase the overall efficiency of the interaction by making each of these subtasks becomes more efficient via new target acquisition techniques or new manipulation techniques. Essentially, the assumption here is that each individual interaction can be independently optimized. But can we make such assumption? In traditional 2D user interfaces, Mandrake and Locke noted that the user acquires a target with a specific goal in mind. Perhaps the wish to click the target. Perhaps the target activates a secondary set of widgets and then they need to click on a second target. Perhaps they wish to reposition it imprecisely or reposition it precisely. They observed that in the context of 2D mouse-based acquisition, the intended manipulation of the target impacts the acquisition performance. Follow-on work by Ruse and Lang replicated these results and analyzed the potential impact on kinematic link endpoint prediction. Their results imply that the potential benefits of new interaction techniques observed during manipulation may not be realized if they result in a corresponding increase in acquisition time for the target to be manipulated. Interactions in VR will differ from those in both real-world and 2D interface. For instance, the controller in VR is an absolute input, while the mouse is a relative input, leading to different acquisition and manipulation behaviors, and some tasks more frequently in 3D were not investigated in 2D. We wonder whether the intended use effects on targeting exist in VR and how it differs from those impacts in 2D. Therefore, in this project, we conducted a control experiment to investigate the existence of this effect in VR. Here is the timeline of a trial in this experiment, and I will introduce our experiment from this figure. First, a trial starts when participants select the start target, which will view the task and calibrates the starting location. When participants correctly select the start target, a primary target appears relatively to the start target's location. The secondary target only appears according to the manipulation that a user or participant plans to do. Here, we define such manipulations as tasks, and we have 5 tasks in this experiment. First is the targeting task. Second is the dual targeting task. The third is the docking task. The fourth one is the throwing task. And the last one is the wheel-orienting task. We adopted a repeating measure within subject design. We focus on 3 independent variables, task, ID, and block, and apply LOVA to analyze the data. Now let's look at our results. For the error rate, The overall rate is below 5%, and we did not find the main effect of task on the error rate. We removed the first block due to a learning effect. Now with the remaining data, it showed that targeting was significantly faster than the other four tasks, and reorienting was found significantly slower than the other tasks. With a significant interaction effect between task and ID, we took a close look at the result. It showed that reorienting was slower than other tasks at all IDs except than throwing at 2.66 speeds, and targeting was significantly faster than dual targeting and reorienting at 1.49 bits and throwing at 2.37 bits. To better understand where the difference between tasks come from, we analyzed the motion kinematics profiles of participants' correct target selections. In order to compare our results to Matrix work, we also use these profiles to compute the following motion kinematics measures: peak velocity, time to the peak velocity, percent of time after peak velocity, and selection velocity. We found that different tasks had different motion characteristics during the acquisition time. I won't detail all here, but the reorienting showed a significant difference from other tasks. For more details, please check our paper. When looking at the Fitzgerald modeling and throughput values, we noticed that slope values B were relatively similar across tasks, but reorienting has a higher y-intercept value A than the other tasks. Unsurprisingly, targeting has the largest throughput, reorienting had the lowest throughput, and throughput values of the other three tasks were similar, a result consistent with the selection time result. The goal of this paper is to explore the impact of intended use on the target acquisition in VR. We found that targeting was significantly faster than other tasks at certain IDs, and reorienting was significantly slower than all other tasks at all IDs except than storing at 2.66 bits. Given that there are significant differences between targeting and reorienting, our hypothesis was supported, and the impact of intended use on target acquisition existed in VR. While I did not talk about the kinematic motion results in details, the analysis showed that reorienting has lowest peak velocity and longest deceleration phase. It implied that participants planned their movement and did not rush during the selection for reorienting. Besides, the Fitzgerald modeling confirmed this by showing that the delay of reorienting was higher and the throughput value of reorienting was slower. So, what do these results mean? Let's look back at Bergstrom's work. The assumption that underlies this success matrix in measuring user performance in VR is that each individual user action can be optimized in isolation from other tasks in the interface. But our results argue that this assumption cannot be made. If different manipulation impacts the time taken for preceding selection, then measuring only the manipulation may overestimate or underestimate benefits of a novel interaction technique in a VR environment. The second point is that we should consider other prospective impacts for designing techniques. Specifically, when we have new interaction techniques available to us, incorporating them into realistic systems requires thinking not just about the individual action that they optimize, but also about their place within and more general impacts on the overall task flow of the user. Our results can be framed into concrete applications and interface design in VR. For instance, considering three manual interfaces above in a VR environment, our results suggest that techniques that use dual targeting and docking may result in a similar selection time prior to the manipulation subtask. In contrast, the technique that leverages reorienting has already taken longer selection time prior to the manipulation. Before I end my talk, I would like to thank my supervisor Ed, who passed away last year. This project started 2 years ago at the beginning of my PhD. We came up with this project when discussing my thesis topic, and Ed was always interested in this idea of how intended use will impact the target's acquisition. This project would not have been possible without him, and I would like to take this time to appreciate his advice, help, and support. To conclude, in this paper, we identified the existence of an effect of intended use on targeting VR. We studied 5 interaction techniques, synthesized their results, and highlighted their implications for design and research in VR. Thank you for attending my talk, and now I'm happy to answer your questions.